Okay, fine. So Ranjit sir is currently working as product designer at Philips India Limited Pune. Prior to it, he worked with Reni South Korea, Siemens Technology India, Bangalore. Ranjit has over 19 years of industrial experience in end-to-end electronics product design and development. He worked on various DSP, FPGA, and processor-based hardware design. He has over 16 years of experience in medical device design, designed X-ray systems, digital X-ray detectors, and clinical chemistry analyzer. He has good knowledge and experience in EMC and reliability. Ranjit has done ME in VLSI and embedded systems from RSCOE Pune, MTech in biomedical engineering from MIT Manipal, and BE in electronics and communication engineering from Bharatiya University, Coimbatore. Ranjit sir has delivered expert lecture on various topics in electronics, biomedical engineering, project selection, and career guidance to engineering B or MedTech students. Delivered lecture to over 14,000 students from over 190 engineering colleges and IEEE SB across India. Ranjit sir has conducted FDP in various topics in electronics and biomedical engineering to engineering college professors. So thank you very much, sir. Sir is going to deliver the particular lecture on the topic of FPGA-based design for SOC application. So thank you and most welcome to the particular session, sir. So now you can start your sessions.
Thank you, sir. Thanks for the introduction and thank you for inviting me for this session. So today, good morning to all. So today I'll be talking to you about FPGA-based, designs for SOC. So where I'll be covering, various topics, starting, from FPGA, where I'll give a brief overview of FPGA architecture.
Excuse me, sir. For 1 minute, can you on your camera so that
Yeah, sure. Yeah, sure,
okay,
sure.
after that you can off your camera.
Yeah, sure. Yeah.
Yeah. And also
Okay.
on your the particular PPT also.
Yeah, PPT, I think you can
It
see,
is
no?
on now.
Yeah,
Yeah, yeah,
yeah.
fine. Yeah,
Okay.
thank you.
Yeah. So I'll be, talking to you, about the overview of FPGA architecture. Then I'll talk about the processors within FPGA, like soft core and hardcore processors there. Then I'll talk about, the need of FPGA based SoCs, and then I will talk about the sync FPGA SoC architecture from Xilinx. There I'll give an overview of the architecture, and then at the end, and I'll talk a bit about some of the applications like camera and image processing, in sync actually, and what are the things that need to be taken care, etc. So if you have any queries during this session, you can stop me and ask me directly, or you can type it in the chat box, and I will answer you at the end of this session. Okay. So now let me tell you a bit on my experience. So I have over 19 years of experience in end-to-end product development. I work on DSP, FPGA, and processor-based design, and also I work on wireless-based hardware designs. And I've also worked in electromagnetic compatibility, in a reliability aspect in product design. I have masters in VLSI and embedded system and biomedical engineering, and I've done B in electronics and communication. So now let us get started. I hope all of you are aware, like what is, the programmable logic and how it evolved. But I'll just briefly, talk about that initially. Okay. So we had this PLDs actually. Okay. So this was developed in the 78. Earlier, these PLD devices were called symbol PLDs or CPLD, and these were very popular, till the beginning of 2000s actually. So at that time, this was used a lot actually, where whenever we want to process some data parallelly, or you need a lot of IO lines, so which is typically difficult in the controllers actually. So if you take any microprocessor or controller, you will not have too many IO lines actually. Really, some of the lines will be dedicated for the memories, but to general purpose IOs will be very limited. And another problem is that when you are want to execute the parallel programming and other things, the processor will be slower. So using this kind of devices like CPLDs are very helpful actually. Okay, and this can also act as an interface between various modules in the system, and finally, to the processor actually. That's how, the design typically looks like. Okay, so then, FPGA was introduced after that actually. Okay, so then FPGA become very popular. And but FPGA also, you can do a lot of tasks actually. So you can have softcore or even hardcore processors were there, possibly, to implement actually, which was there actually, like a power PC, etc., and Vertex series of FPGA from Xilinx. But that was not sufficient actually, really. Those were not really high performance, so those were typically operating up to 400 megahertz or so. Then, with the necessity of, reducing the power consumption and also to optimize the design, there's a need actually, to have FPGAs, with some processors, and to make it like a system on chip actually. So you can have even, unlocked digital converters and a lot of communication interfaces, like, and all those things are possible. And so that's the reason why now Sync is one of the most popular system on chip available in the market, which is very flexible actually. Okay, so a lot of things can be done. Even now you can say, like, to certain extent, FPG is also competing with the DSPs actually. So because you have DSP slices within FPGA, where you can perform various tasks. Okay, so that's the reason, why, when it's important also for you to know actually. So many of you may be, working on, various projects, or want to pursue research and other things actually. So you could always think about, using, this kind of system on chips, very good perform multiple things actually, and it is also quite easy to prototype and so on. Okay, so now let us just, talk about the evolution there actually. So I mean, initially you had a PLD, so a simple PLD actually, where you can't do much things actually. It has got a limited capability, limited logic cells actually. Okay, so then, I mean, CPLD came actually, where you can perform much more task actually. Okay, so, and it's cost effective. Then, FPGA came. So I mean, CPLD also has got limited capability in terms of, the logic cells and all. Okay, whereas, in FPGA you've got large capacity, and you've got a different type of blocks there, specific block for various kind of applications, like DSPs and other things actually. Okay, and also it can support various kind of memory interfaces and high speed interfaces. Okay, even some of the FPGAs, you can even have, over 10 Gbps, kind of interface actually. So you can transfer that data, to that extent actually. Okay, so this is all commonly used actually. Okay, so you can say, like, in certain area, that this is, at a very low end FPGA, so CPLD can also, do certain things actually, what FPGA can do. Okay, but slowly, CPLD is almost out actually now. I mean, it's very rarely used actually. So I mean, FPGA have got all kind of FPGAs, from very low end FPGAs to, high end FPGA, where you can perform a lot of tasks actually. Okay, so if you see the CPLD, you've got you have got two kind of CPLD. I mean, the first one was they started with, simple PLDs, and then you have got CPLDs actually. Okay, so the architecture is, this is different actually, compared to an FPGA, because it has got a simple, very simple architecture, where you can only perform a limited number of tasks actually. Okay, so the configuring of the CPL is again, somewhat similar to FPGA, where typically, you can configure, during your power on actually, where your the the logic will be, in an external memory actually, and when you power on it, typically, it takes actually. Okay, yeah, so I mean, FPGA, is actually, developed, to address the gap actually. Okay, so FPGA has got a lot of benefits actually. It's not only, for you, I mean, for a common application, it's also used in ASIC development, because a lot of prototyping activity is done in the FPGA. It's very important actually, because we need to know. Suppose you are designing an ASIC, okay, for audio signal processing application. So we need to first prove it actually. So whatever your concept is, working perfectly, and whatever you're going to develop, or the operating frequencies, etc., it is sufficient enough. The problem is that, once you have an ASIC, you don't have any flexibility, to change it later. That is the reason why we need to do the prototype initially in the FPGA. So that is really going to help you, how you want to, prove it actually. Okay, later point in time. Another advantage is that, FPGA is that, you've got plenty of, logical elements. Again, it depending on, type of FPGAs, but you have smaller FPGAs with a lesser number of IO lines and lesser logic, which could use for low-end applications. At the same time, the same family, even you can have a FPGA with large number of logic cells and memories and DSP blocks and so on. Actually, with a large amount of IO lines, it can go in even in up to 1,000 or so. Actually, okay. So you can imagine, how this all can bring benefit actually when you're developing a product. So that is one of the biggest benefit FPGA is providing. Whereas if you take a processor, you don't have this many lines, IO lines. Suppose you want to integrate a camera, for example. So you'll have a large number of photodiode arrays, so you need to have so many signal lines actually to to interface actually. Really, of course you can do multiplexing, but in certain applications we won't do that actually. So you'll directly interface where you need say hundreds of IO lines actually. And the configuring is typically done by external memory. Okay, because the earlier there were certain FPGAs where you've got even EPROMs actually, so where you can directly program it, and then once you power on, it will work automatically from there. But nowadays, it's like, you have a PROM, from there, if, FPGA will take the logic and start working actually during the power on. Okay. So again, the difference, different type of FPGAs or families, mainly lying on, what are the different type of, signaling it provides, and also about the logic cells, the memories. So different type of FPGAs about different type of signaling. Lot of differential signaling, high speed signaling, like Ethernet signals, like, or or even PCI Express signals, SATA. All of that is supported by various kind of FPGAs. But again, you need to consider this aspect while you choose the FPGA based on your application, because the FPGA from same family need not support everything actually. So you need to look into this aspect actually. And also you can choose the FPGA with the different operating speeds, because that also will give a benefit in terms of the cost and power consumption. So that's also an advantage you have actually, because in a processor you don't have that much capability to change the a clock actually, but in FPGA you can do in whichever way you like to. That's the biggest advantage. And in processor, you have got one more limitation. Your clock, signals are, in fixed location actually, fixed pins, you can say. So, you can't do much actually on the PCB side actually. But whereas in FPGA, you have got more flexibility where, you can, decide actually, to a certain extent, which lines to be used for clock. Accordingly, you can use it actually. Okay, so that is also very beneficial in terms of, reducing the electromagnetic interferences or even signal integrity kind of issues actually. Okay, so you can choose the one which is based on your application at what speed you want. And and they even there are different type of FPGAs for military or even aerospace application, where it can withstand at a much larger temperature, etc. Okay. Another point is that when you have FPGA, you assume you change an FPGA. Okay, so but you can easily change the design, and it's also quite flexible actually. Okay, so you don't need to look another FPGA for your next version of the product, etc. Whereas if you choose a processor, many time it happens that sometimes the processor may not have larger memory interface, etc. Okay, so you may have to go for another processor which support that. But in case of FPGA, it generally give a lot of flexibility. Yeah? You can even interface 32-bit memories and so on actually, with large capacity, because there will be multiple IO banks in FPGA, so you can have multiple interfaces. So that's going to really help you. Okay, so that is a biggest thing. And also typically you get a good support in developing various kind of designs with FPGA. Okay, so there are different type of FPGAs actually. So one is one-time programmer, reprogrammer, but one-time programmer is not available now actually. So that was there in the beginning actually. So SRAM based FPGA means it will configure during the power up actually. So this is the common FPGAs that is used actually. Okay. The anti-fuse based FPGA or EEPROM or E2PROM, these are all not commonly these are not available at now, present actually. This was there in the very beginning actually. Okay, so when this FPGA was introduced actually, those days actually. Okay, so typically if you see Xilinx or Ultra, now it's called Intel actually. So these are based on SRAM based FPGA. Even so some of the earlier FPGAs got also flash, so you can download your configuration to bitstream file to flash, and it will take it from there actually. So, but anyway, whether you use Chrome or anything, it doesn't make much sense actually. But again, the problem with the Flash is that if you have a large an amount of logic to be implemented, etc., then it will be a challenge actually. Okay, but whereas in SRAM, that's not a problem. You have a flexibility of choosing, from of a different size, or even you can configure from other kind of memories like an AND or NOR also. That is also possible. It's not necessary that you have to configure your FPGA directly from this. You can also configure through a processor or FPGA, or in some cases even from PC. Yeah? Suppose you assume that you have got a graphics card. Okay, so typically most of the graphics cards are based on FPGAs. Okay, so you'll insert in the PCI slot in a PC where it will configure directly from the PC memory actually. So that's also possible. So there are various ways to do that. Okay, so now I'll quickly tell you about the various elements in FPGA. Okay, I've got the various elements. So logic block is one of the important, and that's a basic one. Then you have IO blocks. This is again very important because this IO block also plays a major role. See, one of the major advantage FPGA is providing, compared to microprocessor or DSP, is that typically in a microprocessor or DSP you don't have much flexibility in the IO line voltages. For example, it may be mostly 3.3 volt, or some cases it can go up to 1.8 volt, whereas in FPGA you can use a different voltages, say from 3.3 to 2.5 to 1.8, 1.5, 1.21. All of that is possible, and you can have a different kind of signaling because these are general IO lines, so you can make it as input or you can make it as output, or even some cases you can make those as a differential signal as well. So that's the biggest advantage, and the clock resource are available plenty, and also many of the FPGAs got inbuilt multiplies, different kind of memories, and lot of other features. So that's really helping to use them in various kind of applications. So that's why FPGA is very popular. So this is how in terms of FPGA looks like. Okay, so you've got various logic blocks actually. So this is where you implement the logics. Then you have the IO blocks. So this will spread across the FPGA in all the sides, you can say. So and you can configure it individually. You can decide which voltage you want to use actually. Okay, and also you can decide which type of signal you want to use. Okay, for example, in a processor, you have, if a memory interface is there, that's fixed actually. You can't change at all. But in FPGA, you can interface it to various IO banks actually. That's possible. Okay, so that is very beneficial when you're doing the PCB layout, component placement, etc. Okay, and you've got a clock manager, so you can decide. Suppose you want, use a clock from here. So then you can use the clock, block from the the DCM, from this area somewhere to here if it is available like that actually. Okay, so then you've got plenty of routing channels and a lot of memories available. The random access memory is available, which is highly beneficial for image processing kind, or a communication kind of applications where you need to have a lot of local memories. So this is also a benefit, and the advantage here is that there are a lot of RAM available here, and you can also combine and use it based on your, like, make it a block, like a block RAM based on your type of FPGA that you are using. That's also beneficial for you actually. Yeah? So that's giving a lot of benefit in terms of the access speed. As as in the microprocessor, these are fixed one actually. So there is like the size, there's maybe up to sometime 512 KB, or depends actually. Okay, so you won't have too much available there actually. Okay, but whereas here, if you choose a larger device, you can define actually how much you want, and after that you can use it for something else actually. So the access speed is very fast actually. So that's the biggest benefit you are getting here. Okay, so and also you can have different kind of processors also within it. You can have the softcore processor, the IPs are available actually, or even some of the FPGAs will have hardcore processors. Now in system on chip, hardcore processor is available actually. Okay, so this is how all the the FPGA looks like. Exactly not here like this here. So it is all BGA pack. All the pins will be on the bottom side actually. Okay, on all the new FPGAs, so where you can have a multiple devices connected to it actually, and also it will provide memory at various locations, so which you can use it actually based on your application. And many time the Ethernet MAC and other kind of interface also available within the FPGAs. So that's also giving a lot of benefit actually for you. Okay, so the logic element, this is the smallest thing actually. In FPGA, so this is where you typically start implementing everything. So here you have lookup table, flip flops, and multipliers actually. So the lookup table, this the architecture varies from FPGA to FPGA, so that's not constant actually. So some of the FPGA level has input kind of lookup tables actually, so that is useful for complex applications. Okay, so there are various other type of then you need to connect actually all these logic blocks within the FPGA. Okay, so that is possible through the programmable interconnect there. Okay, so you can have different kind of logic blocks and other things in the FPGA, so you need to consider these aspect while you choose the FPGA. Okay, so this is one of the major thing that need to be looked, again, depending on your application, where you need to have a signal processing or image processing kind of applications, then you need to have a lot of logic elements, and also to have a specialized block and the memories which is needed actually in the FPGA. Okay. Yeah, so there are different type of LUTs available again based on various type of FPGA. So for example, ultra scale devices, it support up to 8 into 6 input type of LUTs actually, and which will have also various number of registers, etc. And this can also be configured. That's possible actually. So in some of the FPGA it will be just 4 input LUT. So it all depending on the type of FPGAs that you will be choosing actually, and that is also important actually. Depending on what kind of application you want to use. Okay. So this is how everything logic element is connected to various IO blocks actually to the FPGA. Okay, and through which you can interface to the external devices, etc. Okay. So again so the routing is done in both the horizontal direction and the vertical direction actually. Okay, so again, when you are choosing, logic to be implemented, or the clock to be used, you need to always see from the board design perspective. Yeah? So sometime you want to, assume this is an FPGA, for example. Yeah. Yeah, so this is a chip, and you are placing all the devices here. So for example, you have a camera signals. Okay, so then naturally you need to use the clock source from here, not from here actually, because that will cause a delay to the thing actually, and it could also create a skew actually on the clock signal. So that's very important actually. So you to consider all these aspects practically. Yeah? Okay, so when you use the evaluation boards, they have taken care of all those things, so you don't have anything to do. But when you are really designing something with FPGAs, you should think about that actually. Okay. Yeah, so IO blocks plays a major role. This is we use to interface various devices, and there will be multiple IO banks in an FPGA, and each of the IO banks can be configured at different voltages. So you can supply voltages to that particular IO block, and the IO block will operate at that actually. So that's a benefit you are having. Yeah? So you can, as I said, told you, from 1 volt to 3.3 volt, you can interface. So if you have some memory, for example, DDR3, and also 1.5 volt is required. Okay, like that actually. Okay, so suppose your signal is the other side device is giving output, say for example at 2.4 volts, so you could easily interface. That's a flexibility that you're getting actually, and you also you can choose which bank can be used for various applications. That's a benefit you'll be getting here. Okay, and also you can configure so like you can have a up and train output, or push pull, or a different kind of output, and also you can define the slew rate, the driver strength, and it support plenty of IO standards actually. Okay, for various kind of devices, and also differential signals. So that's the biggest advantage you're having actually. So finally, these are helping to interface different kind of devices. Okay, and that's why it's so flexible. In processor you don't have all that actually. So that's why FPGA is becoming more and more popular actually. So where you can do anything. You can have any kind of devices interface actually. So the clock is very important part actually. So typically what we do is that we use external oscillator, okay, to FPGA, and internally we will use the PLL to multiply actually. Okay, and then you will generate plenty of clocks actually. So that can be used for internally for the logic, or it can be even used for support, providing the clock to the external sources. For example, you want to have a memory, so you need a clock there, or you want to have various other devices, okay, for example camera, which need clock signal. So all is generated from here, and the advantage is that you can generate clock different frequencies actually. So you've got a more flexibility compared to your processor. So they've got various kind of clocks for local support and for globally actually, and also it support differential clocking actually, that is required for the memory interface or PCI Express interface, etc. So you need so you sometimes clock up to 1.25 or 2.5 gigahertz. All of the things are generated internally. So ideally, speaking, you'll only provide one clock source to FPGA. So typically, from an oscillator, and then that will be multiplied, and remaining clocks will be generated, and that can be used internally and also externally. Okay. So then FPGA support a lot of memories, and of course FPGA has got memories actually like a distributed RAM or block RAM actually. Okay. So and also FPGA has got various memory banks within it, and also FPGA can be interfaced to various type of memories like a DDR, different kind of DDR memories like a DDR2, 3, and the mobile memories, and also like various kind of flash memories like NA and NAND and NOR actually. Again, depending on the FPGA, the internal RAM size might vary actually. So you need to also see the size of the block RAM, and how much memory total is available, but that is beneficial for you. So many time with these memories you can avoid the usage of external memory actually for data sensitive application where you have got a lot of data. Okay. So I mean that is helpful in terms of the cost, and also in terms of the execution, and reduce the latency actually, because everything is within the FPGA. Okay. Yeah, and so this how I mean the block RAM look like actually. So there are I mean block RAM available and also distributed. So RAM available in the FPGA actually. Okay, so this is all internal to the FPGA. So all the clocks that is needed is generated internally actually by the FPGA. Okay. So then you have got various kind of DSP blocks actually. So this is quite popular in many of these FPGAs. For example, Xilinx has got a DSP block called DSP48 actually, so which support 18-bit by 25-bit multiplier, or 14-bit 48-bit accumulator, and so on actually. Okay. So this is also useful, I mean, for various kind of applications. So this is where I mean, DSP is also giving a threat to sorry, I mean FPGA is giving a threat to DSP. So sometime it's really confusing for a person to choose whether to go with FPGA or DSP actually. Okay. So, but of course, in some cases, DSP performs much better than that, because FPGA is not completely designed for DSP application, but they provide the DSP block so that you can use it anyway. Normal kind of applications you can do. For example, you take a camera and all. In camera, typically FPGAs are used many time, so you can do all that things actually. But when you really need a high performance, especially in medical applications and all, many times we use DSPs as well actually. Okay. So now let us talk about various kind of the serial interfaces FPGA is having actually. So as I told you, FPGA provide both CMOS type of signaling and LVDS signaling actually. So it will really provide high speed interfaces. So there are transceivers within the FPGA which is available in a high end FPGA. Okay. So where even you can achieve a throughput of say 32.75 Gbps also. That's also possible. So you can imagine, I mean, in 5G base stations and all this kind of application, you need really high throughput actually. So FPGAs are supported actually. That's where FPGA is useful, because can be configured. They will provide the capability, so you can decide, how many of them you want to use actually. Okay. So that's a benefit actually, and of course, you need to finally, manage everything within the FPGA. So there is a monitor available, so which monitor everything, the power and other things. Yeah? So during the power on, and when you design a system, typically, you do the built-in self-test, right? So all of the things can be possible to implement within the FPGA. And the power management of FPGA is slightly complicated actually, because you need to have proper power sequencing, and assume you're using so many different kind of voltages. This is very important actually for you. Okay. So and the power consumption also, in generally speaking, it's a bit higher actually here. Okay, but again, you can optimize it based on your design, so that there is static power and dynamic power actually. So static power is there by default actually, but dynamic power is depending on your application. So when you're reading or writing a data to a memory, so at that moment, suddenly the power will go up actually, like that actually. Okay. So this is also a factor which you need to consider when you are using in a portable devices, where it will be operated from battery. Yeah? So that's an important aspect which you need to consider. Okay, so the configuration can be done, from various sources actually. Okay, it can be done, from the prompt directly, or it can be done, from PCI Express, etc. These ultra scale support data. So directly, I mean, it can, configure from the PCI Express actually. During the power on, it will take it over actually. And also it can boot through JTAG. Okay, so and a lot of tools are also available internally to check the signals and other things also. So Xilinx, Vivado, and provide all of that actually. Okay, so now comes the processor. Okay, so actually the processor is giving a lot of flexibility ideally. So certain tasks can be done better in a processor compared to FPGA actually. Okay, so that's the reason behind having processor within FPGA. Okay, so concept is there since last say 15 to 20 years actually. So initially, you might have heard about this microblaze, software processor or PowerPC processors, which were there in the Vertex 2 series of FPGAs, for example, from Xilinx actually, from early 2000 onwards. And that was a very popular actually at that time actually. Okay, so and also you have various IPs already provided for for creating this software processor, or even you can create your own software processor. So you need to see actually which one to use again based on your application. Say software processor has got a limited a limitation in terms of the performance, where hardcore processor can give a better performance. At the same time, the cost may go up, and also the FPGA resource already will be used for that. So in the hardware, so you'll have less, the logic elements actually. So you need to decide actually, which kind of processor that you want to go. Okay, so again, everything depending on your application and a bit depending on the logic and depending on the family that you're going to choose actually. Okay. So the hardcore processor are already fixed actually in the FPGA. So that's the design. Software processor, you can configure actually. So you can have IP or you can develop yourself actually. Okay. So again, based on your application, you can have as many as software processor as possible. So if you see like a microblaze, it's an example of software processor from Xilinx or Ultra or Intel, and they have got a Neos actually. So this, but the problem here is that the speed actually. So the speed is low here actually. Okay. So this is a configurable 32-bit processor. This is all based on RISC processor actually, and sometime it can even achieve up to 400 megahertz actually. Okay, so it support a various kind of 3-stage or 5-stage pipeline, and it have a cache, then multiply, and all that barrel shifter. So which is typically useful for filtering or signal processing kind of applications actually. Okay, so you can have your own. I mean, you can get the IPs, or you can have your own, processors actually. So that's possible here. You know, so this software processor is for mid like your medium kind of applications actually. But hardcore processor you'll get a better performance. So if you take a single the system on chip, you just got Cortex processor, so which can even give a performance up to say 1.5 gigahertz. That is possible actually. Okay, and also this kind of processor will give you a lot of communication interface capabilities as well actually. Okay, so and they support various type of interfaces. So that is one of the advantages actually. Okay, so earlier Xilinx used to have this a power PC, a 405. So that is a hardcore processor that was there in the past actually in Vertex 2 series onwards actually. In Vertex 4 also this was there actually. Okay, so but nowadays this is all you can say like obsolete FPGAs actually. So in the latest typically you have a ARM based one actually, so which is better in terms of the performance, etc. Okay, so this will give like a lot of capability to you, where when having processor will give you certain advantages of a processor. At the same time having FPGA within, also will give a lot of flexibility. I mean, you can perform a lot of parallel tasks actually, so we will get benefit from the both sides actually. So that's the reason why the processor cores are getting integrated, and that's becoming very popular, because you can do a lot of things. And another advantage here is that see, typically you take any applications, so certain things will be done in by a processor. And certain things will be done by the FPGA, but having them together, it's the best thing actually. So you have a lot of benefits actually in terms of the number of connections. You can have a smaller PCBs, reduce the power consumption, and also even the cost. And finally improve the reliability. That is also very important actually, when you have a lesser number of component, so you can have better control over, the design or over the manufacturing, etc. Okay, so that is also bringing a lot of, benefits, when you are considering the processor cores actually. I mean, it's giving a lot of advantages. Okay. Yeah, so you have a soft and card, yeah, that I've told you, you have to choose which one you want to use. Okay. Yeah, so this one also, this is, yeah. Okay, so now let us talk about the system on chip actually now. Okay, so I mean, you can have a two kind of system on chip. One is, pure ASIC based one, and another is based on FPGA one actually. So ASIC based one has got like a lot of I mean disadvantages rather than the advantages. The problem with, ASIC based one is, that, I mean, you can't change anything, once, the system on chip is available. It's for one particular application. The development cost and time, everything is really high. But sometimes, the advantage there is that, it's really optimized, yeah? So for high performance application where you have got large volume, that's also a good choice actually, because you don't have any problem there. But the and I assume, that you don't need to change anything and your volume is so high, like automotive industries, etc., where, that makes sense actually. Whereas, the FPGA based one, the performance is good, but it may not be as good as I mean ASIC based one. But, I mean, for low volume applications, or where, you want to have have a changes later, then this is the one which go actually. So there are various kind of, I mean. Processors use here, say, I mean, commonly ARM ANN is used in some cases. Even ARM A53 processors are also used actually, and they provide a lot of, communication interface capabilities actually. Okay, and also, they this provide, various kind of operating system support like Linux, etc. Okay. Sorry. Okay. Yeah, I'll come on this actually at later point actually. Okay. So when integrating, both of the things, in a single, chip is giving a lot of benefit. One is, it is giving, I mean, better computing efficiency actually. Certain things you can do better, in FPGA, and certain things you can do better in a processor, and that will also reduce the total board size. Okay, because you need not have multiple devices actually. You can have a same chip, a single chip actually, rather than a multiple chip actually, and it will also, help you, in reducing the power consumption. And especially this is very useful in terms of, the signal integrity perspective as well. When, you're having too many interfaces, that can also cause signal integrity issues. Will also have, electromagnetic interferences, so from the regulatory perspective also, this is more better actually. Okay. And also, this has got a lot of, peripherals actually, so which is there actually. Okay. So I mean, you can have a common memory here. So you assume, you want to have a, domain, external memory, so that can be used commonly. I mean, so within the system on chip, you can have FPGA which will, take the both ones actually. Okay, so that way it is beneficial. Okay, so this is how it the benefit you are getting actually. So this is the system, typically we were having before, like, you separate interfaces, separate memories, etc., and then you can communicate FPGA to, processor. This is done normally actually. Okay, so now with the help of, system on chip, based on FPGA, so you can have a common memory, you can have a common interface. That's giving a lot of benefit actually. So that's the reason why this is becoming very popular. Sorry, 1 minute. I think the slide I have used is, I mean, the older one. So I'll just stop it, and, I will open the new slide. Sorry for that, actually. Okay. I hope you can see now. Yeah. Okay. So that's main drive, behind using, system on chip-based FPGAs, where, it's bringing the benefit actually in terms of, the capability of both the processor and the FPGA. Okay, so you see, like this is how the architecture of a system on chip ideally looks like. It can have a processor, and it'll have a memory controllers actually, and lot of type of interfaces actually. Okay, so I mean, like I2C SPA, and sometime it will also have data converters like ADC and DSAs, and sometime again depending on the system on chip, you can even have a video processors and a lot of other things. So now what we are achieving is that we are putting all of these things within the FPGA. Okay, and so the architecture is defined. Okay, so the programming subsection or the logic part, you will split actually, and you will have it in everything in a single chip actually, and that's giving the benefit. Okay, if you see, I mean, a system on chip, you have a processor cores there actually. Okay, so and also sometime you will have a DSPs or video processor as well there. So it will also provide internal memories and the memory controllers, to interface external memory, and different kind of high speed interface also provided actually. Okay, then support the external memory interfaces like flash and various kind of DDRs and other things actually. Okay, so a lot of things are provided, and the biggest benefit here is that ADCs and DSCs are also there. So many time in the past, we used to use the controller. So typically, if you see an application, we used to have a smaller controllers. Okay, so I mean the basic controllers, so which take care of a lot of kind of interfaces, and the FPGAs for a high end actually. Now with the help of the system on chip, which is available from both Intel and Xilinx. Okay, so you can also have this kind of interfaces where you can get the data, or you can activate certain devices and so on. Okay, so that's making the things more and more simpler. Okay, so I mean, as I told you before, I mean, ASIC based SoC has got a lot of issues in terms of the cost and the flexibilities and other things. But of course, this is a good when you want really high performance, and when only specific to an application actually. And another advantage this will bring is that sometime the power consumption can also be reduced, because you when you're using a generic SoC from Xilinx or Intel, they need some power consumption by default static power. Okay, but at the same time, the performance implement, the optimization may not be that much possible actually, whereas in ASIC, base SoC it is already done, but you need to think about the other aspects. So the volume should be really high, the cost of you can't do anything later. Okay, so you have to think about the aspects, all these aspects while you decide actually. Okay, so FPGA based ASICs are very flexible. So that's the reason why, I mean, this is becoming more and more popular. And also for the ASIC design, also the initial things are done in the FPGA based. We are proving our design and everything, and then only we are going for the ASIC based, designs actually. Okay. So there are various kind of I mean available actually in the system on chip available. So there are various blocks actually, like the processor blocks and the logic element blocks, which will be connected internally, and also there will be a lot of memory controllers and various kind of interfaces available. So if you take a sync, I mean they, typically based on A9, and A53 is also there in some of the varieties of sync actually. Okay, so even I mean the programmable chip with the RF interface is also available from Xilinx actually, even Altera. So this is all really giving a lot of benefits. It's giving the benefit of a system on a chip. At the same time, you've got a lot of programming capability. You can change the things actually as and when you need. So that's the biggest benefit you're getting, and that's a need actually typically in any kind of. So for example, you're doing a machine vision system where your camera could change anytime. Okay, so if you have a ASIC based SoC, you can't change because you need support certain kind of interfaces and so on. But in the SoC FPGA based one, you can have always the flexibility of have a different kind of cameras. Okay, so that these are the biggest benefit. When your design is not certain, or you want to have a different kind of camera for various kind of applications, then it make a lot of sense actually. To use FPGA based ones actually. Okay, and also this provide a lot of local memories actually, and the various debuggable tools are available, and the reset block is also there here actually, to reset actually. And yeah, of course it can generate different kind of clocks like an FPGA, and it support various kind of interfaces and general purpose IOs and so on actually. Okay, so the key strength, if you say like the I mean you can design everything quickly. Okay, system on chip, you can decide, you need not fabricate separately, because this SOC, I mean FPGA based SOC is readily available. You can just buy it and use it. You need not go for fabrication, and it's flexible because you can change anything actually whenever you need, and you can reconfigure multiple times. Okay. Yeah, when you say like the investment cost, I mean everything is less here. The design life cycle and all the things are very less actually here. And if you have certain issues in the design, it's easy to fix. But in case of an ASIC based SoC, if there is an issue, you don't have any choice actually. You have to discard actually, all the chips that you have made. But here, since you are designing it, you can always change it actually. That's possible in the field. So that's a benefit that is bringing. Okay. So the here, when you're designing an SoC in FPGA, you need to follow certain things actually. So we need to partition properly whether the processor or in the programmable element actually. Okay. So I mean, sometime it's good to use the block RAM actually instead of distributed RAM. So where the all the memory will be around that, and I mean it's also good to use the DSP block which is available. Okay. So and also you need to think about using what kind of IO interface you need to use accordingly. Okay. So there are various kind of IO blocks available, and also the interfaces available, so you need to use it wisely actually based on that. So you need to think about all these aspects while you're choosing actually and designing. So there are limitations also here. I mean, one is see like if you're really comparing the Intel x86 kind of processors, yeah, of course I mean these are not reaching to that extent actually. Okay. So that's the thing actually. So to reach that extent, you need to have a multiple SoCs, and also, I mean, that's extremely expensive actually. But at the same time, this is bringing a lot of benefits as well actually, compared to that. So and also you've got a good software environment, in the Intel x86 based system. But you can also expand all those things actually, by having a larger interface. That's why many time, when you say the cloud also, you typically, have very high end process and this kind of, system on chips available there, and sometimes GPUs, or even in graphics card also. Sometimes, you'll use both the system on chip FPGAs and graphics card, so certain things can be distributed to use the best out of, both actually. So that's a goal actually. So you have to be very clear. So I mean, sometimes the cost of PC, you want to have a performance with an FPGA based ASIC SoC, so it may not be possible actually. Okay, so you need to be very clear, like what you want to do. But many time, what we do use both of them, so to have better best out of each of it, and so to have a better performance actually. Okay. So now let us talk a bit on the Sync SoC. So this is very popular system on chip from Xilinx actually. So similarly, Intel also has got another one actually. So I'm focusing only Xilinx one actually. Okay. So it has got the single or dual core, ARM Cortex A9 processor. So even new Sync series has got even A53 and all. Actually, up to quad core is also available. Okay, and programmable logic element is available in a single chip actually. Okay. So this processor has got on-chip memory, and it support a lot of external memory interfaces, which I'll talk about soon actually. So this is giving a lot of flexibility to you. Okay, so you can get the benefit of both the processor as well as the FPGA. So typically the memory, everything is interfaced from the processor side actually, and that can take care of all that actually. Okay, and a lot of logic, so, it's implemented the logical element here. Okay, so the in the programmable logic part of it actually. So I mean, if you want to implement something, parallel task or high speed kind of things, you can implement it in the programmable logic part, and the other things like data flow kind of things, or it's various you want to implement various kind of software routines. All that can be interfaced in the implemented in the processor subsystem part, and these are all connected through XI interface actually. Okay. So typically, you will, the boot the processor first actually, and after that only you will boot the programmable logic element actually. So that's how it is done actually typically. Okay. So again, you need to see when you want to use. I mean, you have to always think about your application and choose it. It's not always wise to use this thing. The reason is that, of course, this is a bit expensive actually. So sometimes it happens that, in your design, you can have a smaller processor which may cost say few hundred rupees. Okay, and then you can have a normal FPGAs that may serve your purpose. Okay. Though your I mean the PCB will be a little larger, but from the cost perspective, so we need to really see actually what all things you need to do. Suppose you need to do a lot of high speed or a lot of parallel task actually, and then you need to do a lot of sequential task. Yeah, in that such cases, this is useful actually. Okay. So you need to think about really about that. So blindly, whenever you use anything, you need to have a clear, understanding, and you need to practically see. So even in an ARM processor nowadays, you get, in say like a 300, 400 rupees also. It's possible actually. At the same time, the smaller FPG also available, you know, lesser cost like, 1,000 rupees or, something like that, So that will give a lot of benefit actually in terms of the cost. But this is typically used when you have a really high speed or a lot of parallel tasks to be done. Okay, so this is not for normal basic control kind of applications which can be easily done by smaller devices. Okay, so yeah, so this is a really behaving, this is our sync architecture. Like, you have a programmer, the substitute, this here processor and the logic elements actually. So this is how it looks like actually. So this is really giving benefit in optimizing the things and reducing the total number of components, and finally it's helping in the reliability actually. So having lesser number of components and having lesser number of interface is always good actually to have a better reliability. So this is going bringing that actually. But as I told earlier, so you need to choose it based on what you want to do and whether it's really worth actually to use that. That's important actually, because the power keys part of this kind of device are not simple. You need to have multiple voltage regulators, multiple a lot of power sequencing, the clocking, all that is quite expensive actually, really to do in practically. Yeah? It's not that simple at all. Then simple FPGAs or processor, there it is much simpler. Okay, so it's not the component, so you should think from the end to end actually. Okay, so you have to see really what are the benefit it is bringing, what are the challenges that is bringing, and then you need to really see is it really worth it. So that's how you should always look actually. So it support various kind of memory interfaces, and also, I mean, like a DDR kind of interface and all the flash interface actually. Okay. So it support various RTOSes and so on actually. Okay. So this is a bit of this is how your AXA interface looks like actually. So this is interface to the programming enablement actually. So okay. So this is typically used for I mean, say sequential task. This is for parallel task and high speed task actually. Okay. So you want to do a lot of calculation, this is the place we want to do more actually. So the processor is the main thing actually in this actually. So that there are multiple things within the processor here actually. Okay, like you when have a core processors there actually, and also that is providing a lot of external kind of interfaces, like which we'll talk soon actually, and also that there are a lot of memories available actually. So that's bringing a lot of value actually of using this. Okay, so your the software will run on the processor part, and then then you can have a various peripherals implemented here actually, and it all connected through AXI. Okay, and internally also you have some memories available actually. Okay, so you need to really I mean see actually where to implement what actually. That is very important actually. Okay. So when we talk about the camera, we'll talk more on that actually. So that's very important. Okay. I mean, you need to really partition actually. I mean, processor part you can consider as a software, and the logic part you can consider as a hardware, and you need to decide, what to do where actually. That's very important actually. And also this processor provide an acceleration engine like a Neon processor, etc. So that's also the benefit, where you can do certain tasks actually. And the Xilinx also provide a lot of soft IPs, so which can be used actually so for various applications. So you do not really develop everything actually. So you have a lot of things which is already available. You can get the license from them, and you can use that actually. Okay. So combining all of the things is bringing a lot of benefits. One is you can have a simple design. You can reduce power consumption. Also, you can reduce the complexity in the PCB. Sometimes what happens is that when you have two separate devices, you need a lot of connection in between. Okay, and that also will increase the PCB complexity, because you may have to go for more layers of PCB. This will create a lot of challenges in terms of signal integrity. Finally, that could affect your EMI EMC performance. All of that can be optimized. So These are the benefit. You assume, you want to have a small camera, you take a mobile phone, nowadays you want everything to very small, right? So having more things, means it will increase the weight, it will also increase, the size and all that. And so that's where, all those things are adding benefit actually. But at the same time, that's also bringing a lot of, challenges in terms of various design aspects actually. Okay. So we need to see that. Okay, now let us look at two different FPGAs in the Sync family. I'm talking only about the 7000 series. There are much more than that actually with RF and all. Actually, I'm not even talking about that actually. Okay, so there are various thing actually here, various type of processors available. Even it can go up to 1 gigahertz. In new versions it can even go up to 1.5 gigahertz. That is possible. It's providing a neon engine. Okay, so you can prosper do a lot of things. It provide caches, L1, L2 and so on actually. And one chip memory is also available. It support various memory interfaces, and now you can choose different type of devices, huh? So based on the logic elements, based on the DSP slices, and whether you need a PCI Express, huh? All those things need to be considered when you are choosing actually. That's very important. And you can also see how much memory you need. I mean the block RAM available, you can see that actually here. Okay, and also these are the speed grades that you need to choose. You need to see different speed grades, and whether to use in commercial, extended temperature industry. Accordingly you can choose actually. So there are special package for that. Okay, so that's important. Yeah, so this is a bit on the details. So it has got ARM processors, then a neon engine is also processed, so it's acting like a co-processor there. Then you will have a cache, then on-chip memory, and it support various interfaces, like DDR kind of memories, and also it support various flash memories, etc. So that's also beneficial actually. Okay, and it's about various type of peripherals, like a CAN, so which is not there in the FPGA typically. Okay, so that's beneficial. CAN is used in various kind of applications, so that's a benefit there. And Ethernet interfaces, USB, a lot of things. Yeah? So this is really beneficial. For people who are using this actually. So that's really giving a lot of benefit actually when you're having a complex devices with multiple type of interfaces required. Okay, so you have a programmable logic part actually. So here typically, I mean, again, this is based on CLBs actually, and also you have got a block RAM and DSP blocks are available which you can use, and it support a lot of voltages actually interfaces. Okay, and it has even PCI Express and ADCs and so on actually. Okay, so this is how the architecture. So this is the processor part actually. It's processing subsystem, and this is the programmable part actually. And this is how the interface looks like actually. You have multi-core here actually. Okay, the process, and with the neon interface and everything actually, and which is finally interface to various external type of peripherals actually. So which is very beneficial. At the same time, through AXI interfaces, it is interface to the programmable part actually. So you can perform the task, do it here, and finally you can interface with external devices. So that's the biggest advantage actually. And it also provide some memory inside actually, so that is also beneficial actually for some kind of applications. Okay, so it has got the processor part has got various blocks actually. So the first one is the processor block itself, then you have memory interface, peripheral interface, and it interconnect actually. Okay, so this is where your ARM processor is there actually, and also this is coming with a Neon coprocessor, so which is connected actually to the processor, and it also has the cache that's available actually. Okay. So Neon processor is typically useful for a graphics kind of application. So this is a media and signal processing architecture. This is based on SMAMT architecture. So that's giving a lot of benefit when you want to perform signal processing algorithms actually. Okay, and it support various type of data types, and that's again beneficial like floating point. And also when in high precision kind of applications, this giving a lot of benefits actually. Okay, so this has got various kind of timers which also there, and also it support various kind of external memory interfaces as well. It provide a cache. Okay, so you can use that. Okay, so there's a bit more details about that actually. Again, depending on the different speed grades and so on actually. Okay, So then it support memory interface to different kind of memories, DDR3, DDR3L, and LPDDR2, and various kind of flash memories. So that's the biggest benefit it is having actually, and it support up to say 32 byte, 32-bit interfaces actually. Okay, and it can have provide up to 1 GB address space, and all that is useful actually in various kind of applications. Okay, yeah. So there's a bit more on the various type of memory interfaces that it support actually. Then you have got a various IO peripherals here. So this is important. So they have Ethernet MAC available within this actually gigabit Ethernet. So that's a benefit actually for you, and even USB. So USB is typically not available in FPGA, but that is there actually. So that's again giving a lot of benefit to you actually. And CAN interface, so which is very popular in automotive for other control kind of applications where this you use it as UART and a lot of IO bits and so on actually. So you can't even imagine 118 IO line from a processor part actually alone. So that's not possible. But this is having that much actually. So that's giving a lot of benefit to you. Okay. It's about various memory interface, but all of them are interface to AXI protocol actually. So that's a fast interface actually, so that you can transfer data at a high speed actually. Okay, so that's a benefit it is bringing. And also it's about various external interfaces. As I told earlier, it's about various kind of memory actually. Okay, so AXI port is the main thing here because that's the interface that we use between the programmable logic element part and the processor subsystem. So that's it's based on architecture actually, standard you can say actually. So it's advanced external interface actually. So that will help you to transfer data at high speed actually. Between these elements actually. So where it will provide an interconnect actually. So through that interconnect and interface, you can transfer the data actually. Okay, between these AXI interfaces. So all these interfaces are possible within the HBase using this interface. Okay. So there are different type of AXI interfaces. Like one is general purpose AXI, so where you have a 32-bit data bus actually. It's for a low to medium rate communication actually between the logic element and the processor subsystem. Then you have accelerator port actually, so that is supporting up to say 64 bits actually. Okay. Then you have high performance port is also available with the FIFO buffers actually, so that you can really transfer the data at high throughput even at 64-bit interface actually. Okay. Then it has got an accelerator a coherency port actually. Okay, so this is useful to improve the performance actually. Okay, and this again you provide the low latency actually. So this is a bit on the interface part actually, so which is typically from the data sheet. Okay, so now the programmable logic part, you see like it has got 8 local LUT base actually, CLBs. Okay, and it also have a block RAM and adders are available, and it has DSP slice. You have multiplication possible, then 48-bit adder accumulator is available, and also it support various type of IO standards. So that's another benefit it is have providing actually. So it also has got ADCs which is integrated actually. So this is bit on the lookup tables and slices that is there actually. Okay, so it also have 64-bit RAM and shift registers etc. there. And like in FPGA, this also has got CLBs and the various slices, etc. Actually, so okay, so that is also within the programming logic element actually, and it is made up of that actually. Okay, so this is how it looks like. Yeah? So this is the various IO blocks actually, and these are the the logic elements actually there. Okay, and these are the configured logic box. Right? So the, this is giving a benefit where you can configure or do various tasks, and directly it can be given to the IO block actually. Okay, so that's giving the flexibility. So the lookup table is also I mean support up to say 6 input actually, and it has got the various memories and shift registers are available actually, and the switch matrix is giving better connectivity actually between the CLBs and others, other resource actually within that actually, and it also has got carry logic actually. All that is available. Okay, so the next thing is a block RAM actually. So this about dual port 36 KB, block RAM actually. Okay, so and this has also got a FIFO logic which is already there actually. So that's giving benefit actually. So there are lot of block RAMs available actually. Again, depending on the type of the singer which you are choosing actually. Okay, and you can change the data width here actually. So that's also possible. So that can be decided based on your requirement and application. It will also provide the simple dual port mode actually. Okay, so where you can have a a data width of say 18 bits or 36 bits, etc. So it also has got a distributed RAM actually. So the sometimes distributed RAM is also useful actually, because you can do various task, or you can use it actually randomly in some location actually. Okay, you can have a small memories actually, where you can overall improve the efficiency, and the placement will be more flexible actually. Okay, it has got a FIFO controller which is already there actually. Okay, the next is the processor. So here this thing 7000 series, I've got a Cortex A9 as well as A53. So I'm not focusing on that actually. So okay, so if it has got Cortex A9 dual core, and also it has got Neon processor engine memory management unit, and the L1 L2 caches. All those things are available actually. Okay. So this is helping to have a different kind of interface, and also this interface through the the programmable logical the block of the SoC. Okay. And also this has got the flexible connectivity actually, and 54 pins are also provided for external memory interface actually. Okay, external multiplex input output interface, that is also there. So that is also giving you a lot of freedom. Okay, so these are the various external interface that's commonly used actually and available here. You can say you have SPA, I2C, all of the things are there actually. So this you can't find it in a normal FPGA. Okay, of course Gigi and all is there in the FPGA, but here you have got all of that actually. Okay, so that means you can have any kind of interface in simple way actually. Okay. So the general purpose IO, it's a biggest benefit actually, of this FPGAs, the system on chip actually. So you can configure, and you can have a different type of signaling available actually. A signal into differential kind of signaling, and also you can choose the voltage actually in a various based on various type of applications. Then it provides a communication interface like called a GTXS. This is a really high speed interface actually, where you can even transfer data up to 12.5 Gbps. It's used for PCI Express and various other type of high speed communications actually. Okay, so all this clock that is needed is generated internally. Okay, so this is mainly important networking kind of application. So then it has got a clock management unit actually, since it has to generate really at a high speed clock. It has got lot of buffers in input, and also the clock generation is also done internally in such a way that the clock skew, or and the errors etc can be reduced actually. That's very important actually. Okay, because you need to provide the clock for all these interfaces. For example, you are using PCI, so you need to provide the transmit clock actually from the system on chip actually. That's where it is important. Okay, so yeah, of course in a memory interface, it's about a really large memory interface actually. Okay, and the speed also you can achieve is it's really good actually here with the help of this thing. Okay, so it's about various type of memories, and you can also choose the type of memory that you want actually. And it has got inbuilt transceivers for data transfer. So it can support up to say 12.5 Gbps in case of GTX type of transceivers. But this is depending on the FPGA that you're sorry, the system on chip that you're choosing. Yeah, it's not standard. Somewhere it is GTP where you can achieve a throughput up to 66.25 Gbps actually. Okay, so all the corrections and the noise protection, all those things are part of internal to this transceivers actually. So you don't need to do really anything there actually. Okay, so it does all the serial to parallel conversions, etc. And it also use encoding schema, various encoding schema. So 8-bit, 10-bit, 64-bit, 66-bit, which is already used actually. Okay, and the clock, but the clock that is needed to be generated internally actually. So that's very important actually. So the receiver side also it is similar actually. So you'll get the receiver clock, and also you need to do the decoding all that actually. So that's also done there actually, and also use the various encoding schemes here actually. Okay. So which is also choosable. You can decide actually. Then the next part is DSP slice actually. So it provides a lot of functionality in terms of multiplication, multiply, and accumulate. The barrel shifter, all those things are available there actually. Okay, and the DSP48 even, that is a common slice that is used by Xilinx actually in their FPGAs actually. So this can be used for various kind of DSP applications. It has got dedicated 25 into 18-bit multiplier and so on actually, and 14-bit 48-bit accumulator, etc. Okay, so this is also good enough for certain kind of signal processing applications actually. Setup. And so the booting, first, you'll have a boot RAM actually, and then you'll have a boot, memory will be there actually. So during power up, you'll take the data actually, and then we'll have a bootloader actually. Okay, so you can use the programmable read or memory or NAND or NOR flash actually. Okay, so you'll have the code actually for both the processor as well as for the logic element part actually for the FPGAs actually. Okay, so and then you can it will program it, or even you can program it through JTAG actually. So that is also possible. So this is how the design flow, like you need to have a design, requirement, then you need to design, specify it what you need to do. Then in the system design you need to really split actually. You need to decide when you say software means it will be done in the processor part, and then in the hardware you want to decide what to be done in the software and what to be done in the hardware. Okay, and then you develop in parallel, and then finally integrate all of that actually. So that's how you typically do actually. Okay, so we have to see actually all the high performance or parallel task you need to do it in the FPGA, and the sequential ones, or where the control part you can do it in the processor part actually. So you need to think and do accordingly. Okay, so the software partitioning and hardware partitioning is an important aspect actually, because that's really going to give you the final performance actually. So you need to see in a way to perform what actually. Okay, so this is how you need to do actually. So you have a various functionality, so you need to decide which module will be implemented where in the programmable logic element, that's a hardware, or the processor actually. So you need to decide actually. So that is something which you need to do. Okay, so based on what you need, and accordingly you have to develop separately, and then finally integrate all of them, and this is going to affect the final performance actually. Okay, now let us talk about the camera. This is an example. Okay, so if you take a camera, you have typically you get output, and then you need to do a lot of image corrections actually. Okay, typically this is done in the programmable logic part actually, because it's very important actually to perform all these tasks in real time. Okay, because you assume you have got a machine vision camera where you get something, but that's not that, whatever data you get, that may not be enough. So you need to really do a lot of processing. Okay, and then finally get it on your monitor. So all these things is done in the programmable element part of logic element part of your system on chip actually. And the other controller, so you need to control the camera, you need to finally store the data, and maybe you need to also sometime do some corrections. A correction means some control signals will be there about thresholding. So that's where you can use actually this FPGA, or even finally you want to send the data to a PC, and all those things you can use actually. Okay, and Xilinx also provide the logic or IP actually for the video processing applications actually. So you could use these IPs, okay, for various applications. So there are many more, you will get it actually. Okay, So I mean, why, I mean, what are the benefit that you're going to get here is that, you can do a lot of the processing part, the programmable and logic part actually, and also, the decision making, like, in a white balance or exposure control, all those things can be done in the processor part actually. Okay, which is not too much, I mean, data, there actually. So it's only the control part that can be done there actually. Okay, and also Xilinx provide the IP cores, and various IP cores are already available, so which you could use it actually. Okay, so a lot of, tasks typically, you do here actually, like, you need to do defect pixel correction, color filter, and all that things actually. Okay, so a lot of things, you can do it, in the the programmable element actually, and the control part, the balancing or other things, auto exposure control, etc. You can do it in the processor part of it actually. Okay. So yeah, so the various part. So these are the things typically, you see the programmable logic element, you do the actual processing. Yeah. So here typically you do the control and other things actually, the balancing. Yeah, where, you don't have much data to do and other things. The gain control and other things actually. But this is where, you need to really work on the pixels actually. So where you need, high speed. I mean, performance capabilities and all actually. So that's the reason why, it's separated like that. Okay. So here you need a lot of, parallel things, and typically you see in the, I mean, image processing or video processing, you have pixels, and, you have objects and other things. So you have got a lot of data here. Okay, so accordingly, you need a, the your processor, the FPGA should have the capability, the programmable logic element part of it actually. Okay, so that's the reason, I mean, it is plated accordingly actually. Okay, so you've got a lot of algorithm and the IPs available for this kind of applications. Okay, yeah. With that I've done now, we can now go for the question and answer session. Feel free to ask any questions. Okay. Yeah, some questions are already there actually. See the memory. So you see, the one is external memory. So external memory means, like, for example, you are getting data from a camera. Sometime if the camera data is really large, the block RAM in the FPGAs will not be sufficient enough. In that case, what we need to do is that we have to, I mean, use external memory like a DDR2 or 3. Yeah. So for buffering actually, okay, because you need to take, put the data there, then, you need to process, and, after processing, I mean, when the next frame comes, you need to, again read the data and put the next frame there, like that. So internal memories are used only for local, this thing, where, you will not have much memories available. For some time, you need to really to have external memory like a DDR2 or 3. So internal memory is suitable when you have a limited amount of data. So then you can use the block RAM or distributed memory within there actually. Hope that answer your question actually. So these are the two type. The other memory what I am talking is the flash memory. That is only for configuration purpose. Proper programmable read-only memory or flash memory. And DDR is required when you have a large amount of data. And block RAM can be used for a simple data. Suppose you have a smaller camera, for example. So then you can manage with your block RAM actually. Okay. But when you have a larger, memory, then the block RAM won't be enough, because, we have to use the block RAM for other tasks as well actually. Okay. So typically, to develop SoC, if you are from Xilinx, you have got a Vivado tools actually, and they have also software development kits, for the processor, which you could use actually. And to be, clear, this, boards nowadays, is not really expensive, and also Xilinx or even Intel has got university programs where, the college professors could, get these boards, in the much discounted rate. You could think about that aspect actually, or you could think of, having, a lab in your college, in partnership with Xilinx or Intel. So they support all of it actually. So that's a way, you could think about that. So the tools are available, so which you can get with the evaluation boards actually, and that's not really that expensive actually. Okay.
Excuse me, sir.
Yeah, please go ahead.
Sir, actually, we do have one more question from Miss Panda.
Yeah,
She dropped a question in chat box. I'm
yeah,
reading for you.
yeah.
How to calculate latency cost because of the communication between PS and PL interface in
Oh, okay.
Designer?
See the I mean there are tools available actually. One is in the Vivado environment itself, you have tools available to do that actually. Say for example, you can have with the Vivado you can access see actually at what time you got the data actually of one unit to another actually. So that is typically used actually. It's typically like an FPGA where in an FPGA you process the data in various blocks, right? I mean, so then you can see at what stage what is done actually. So the Vivado has got the capability actually, so you could use that for that actually. I hope that answers your question.
Uh, Hello,
So
sir. Good
yeah,
morning.
yeah. Good morning, sir.
Good morning, sir. Sir, I want to ask some question.
Yeah, please go ahead.
Sir, actually, one of the things you have shown, I have gone through all the slides. My question is, recently Xilinx has introduced two FPGA, like one is Pink board, one is Jink board. So can you
Okay.
please tell that whenever you are using that Pink board, we are using some Python programming, and that Python programming, whether that Python program, just like we are writing Verilog and VHDL, same type of things can we synthesize and implement? Can you please?
Yes, yeah, yes, I think that is possible actually. I mean, even MATLAB can be also used because they are all providing, third-party support actually, where, you can have a MATLAB or, I mean, or even, you sometime Python or even C, and then it will convert. It all depending on the third-party tools actually. So they will directly convert that actually. It is possible actually.
Uh, Sir, can you please tell that what is that basic difference between this Jink and Pink board? Whether almost are same or
No, Pink, I'm not very sure actually. I mean, I've not, seen on that. Sync, I can talk actually. The other one, I'm not, very clear, sure actually on that.
okay, sir. Sir,
Sorry, yeah. So
okay,
Sync,
another.
Sync typically, Sync itself, you have got a wide varieties. See, what I told is the basic Sync actually. There are RF based Sync also, which has got, the RF modules within that actually, which is used in mobile kind of applications. Okay. And there are even quad core and even octa core is also under development actually, so there are varieties of it actually. Okay, so these
Yes,
are all
yes.
really high performance ones, so these are used mainly in communication image processing kind of applications, wherein you need to process large amount of data, all that kind of things actually.
Sir, I
And
want to ask another one question.
yeah,
Hello.
please go
Sir,
ahead.
actually, that as you are know something about FPGA more details, I am asking this. So, whenever as a student, when I was a student, I seen that XC4000 family from Xilinx. Then after I see that Spartan 3, Spartan 6, then Vortex, all these series. So, what is the basic difference of all these series of the family? Whether
It's,
all
it's,
are
See, everything is upgraded version. You can say like it will depending on the logic block. So the logic block earlier were simpler, and it's becoming more and more complex once the next generation comes actually. Okay, and also, in the newer generation, the power consumption is going down actually. Okay, so you have to understand one thing. FPGA the power consumption is typically higher compared to a processor. Okay, in the earlier designs. Okay, so now with the help of better configured logical block and I mean, better semiconductor technology, the power consumption is going down. And so that is going from, say, like a Spartan 3, the power consumption was more, performance was not up to the mark. Okay. Then when it comes to Spartan 6, it's better. Then Vertex is even better, actually. Like that, actually, it's going on up, actually. Kintex is slightly, Vertex series is better, actually, but Kintex is much better than Spartan, actually, like that, actually. Okay, so the differences in the architecture, how is the logic block, how is the lookup tables actually, and what are the additional elements like the block RAM and various kind of DSP slices and other type of communication interfaces. For example, this high-speed GTX interfaces were not there in Spartan 3, but it is there in Spartan 6. Okay, so if you need to have a say PCI Express interface, you cannot use Spartan 6, 3 actually. You need a 6 actually. So like that
yes,
actually. So they keep on increasing actually. The flexibility actually.
yes, yes,
So that's a main difference actually, and the power consumption is a major thing, because earlier power consumption was really high actually. But one way if you see it there they supported the logic voltage. I mean the voltages also is different. So nowadays you can have up to 1 volt interface to 3.3 is possible. Yeah.
yes. Sir, actually, whatever the things you are telling about that some LUT and slices. that inside that CLB, some of the architecture it is showing slice inside the slice, some LUT is there, and some of
Yeah.
the architecture LUT under ka bhi slice hai. Is this true? Or
No. It depends. I mean, see, like it depending on the type of FPGAs that is used, and so I mean, there is nothing, I mean, defined, I mean, from I mean, in that way, from there is no standard as such actually. So typically, the lookup table can be decided, by the FPGA maker actually. Okay, so they typically consider that actually depending on how they want to achieve the performance and how they want to optimize their design actually. Okay, so if you go to all Intel or Ultra FPGA, it is different actually. So it's not same actually. And even in Xilinx also, family to family, it varies actually. Earlier Spartan family to Kintex or Itrix, it's different actually.
that means slice and LUT that is not exactly same in all the
Yeah,
FPGA.
no, it is not all the same. Yeah.
Yeah, yeah. Thank you, sir. Thank you.
Yeah, welcome. Yeah, there are some more questions actually. A white paper, you probably need to explore actually. So I've, used some of, the books actually. I think probably, you can search there, and there are a lot of books are available actually on this SoC actually. I mean, of course, been FPGA is used a lot in IoT. IoT, especially in the node side, it will not be used because the power consumption is bit higher actually. But in some way applications, for example, you take the case of machine vision camera systems, or even the traffic cameras. So their FPGAs are used. Sync is commonly used actually there. It's possible, because there the power consumption is not that critical, but it's simple, the temperature monitoring or pressure monitoring kind of things. You will never use FPGA because the power consumption is more, the cost is more. Okay, but if you take the router or the cloud, FPGA is used actually, because FPGA is required there actually. The processor, x86 processor alone is not enough actually, so it's used. So when you say IoT, you have a node, router, and cloud actually. In node, again, depending on if it is an image processing kind of applications, of course, I mean, FPGAs will be used actually. Otherwise, sometimes DSPs also will be used actually.
Thank you, sir. I'd
Yeah,
like to request our audience, if they have any further queries, they can directly put upon their queries to sir, or they can drop their questions in chat box. Sir, well, I think audience don't have any further queries.
yeah.
Sir, thank you so much for this informative session. Time is very precious, and you spent your valuable time among us delivering informative ideas upon FPGA based design for SoC applications. It was really an informative and inspiring session. Thank you so much for your valuable time.
Thank you, ma'am.
And dear audience, the feedback link is already shared in the chat box. Please do use the link and give your feedbacks as well as attendance. Thank you, Ranjit sir.
Yeah, welcome. Yeah. So if you have any questions, you can reach out to me always. So you can search my name, in Google, and you can find my LinkedIn profile.
Okay, yes sir, yes sir. Fine sir.
Yeah. Thank you all. Thanks for joining, and thanks for the question.
Thank you sir. Thank you so much for your time.
You're welcome. Bye.
Bye sir. Dear audience, now we are at the end of session number 13, and again we will meet at 11:40 a.m. The session number 4, which will be delivered by the research person Dr. Ashish Raman upon the topic design of on-chip oscillators, its challenges as well as perspectives. So again we will all meet at 11:40. Please, if you want to leave now, you may leave, but please join at 11:35 so that the session will sharp start at 11:40 a.m. Link has been already shared for session number 13. Please use the link and give your feedbacks. Thank you for your cooperation till now. Again, we will meet at 11:35 a.m. for the session number 14. Thank you all.